Good morning, everyone. Our next presentation will be developed by Oscar Medina. Oscar is a petroleum engineer with an honorary degree from the National University of Colombia. Doctoral student in engineering, energy system and same university, and doctoral student in chemistry and the University of Granada, Spanish. Research and has more than 4 years of experience in nanotechnology applied to the oil and gas industry, synthesis and characterization of nanomaterials, IUR and EUR process. Author for more than 20 scientific articles, published a patent, a book chapter, and other international events. Many thanks, Oscar Medina, from beginning with the use today from your presentation. Thank you.
Hi, and good day to everyone. For me, it's an honor being here and have the opportunity to share with all of you the most recent advances of my doctoral thesis focused on the effect of the morphology and strong metal support interactions of nickel, palladium, and ceria nanoparticles for the thermocatalytic oxidation of asphaltenes at different pressures. This work has been developed and completed in my faculty at the Universidad Nacional de Colombia and the Universidad de Granada.
Well, asphaltenes are known as the heaviest fraction of crude oil. Because they are extremely polar and present high molecular weights, their proper removal is of significance to enhance crude oil production technologies. The injection of air or oxygen-rich gases is by far one of the most widespread methods used for producing heavy and extra-heavy crude oils. Nevertheless, limited by the combustion front stability and the efficiency of combustion, pyrolysis, and oxidation reactions, asphaltenes converts mainly into coke, and advanced strategies are needed to circumvent this problem. The catalytic oxidation of asphaltenes using nanoparticles is an attractive idea. Nanoparticles present several properties and can improve considerably the potential of the thermal methods to decompose the asphaltenes and produce gases with added value. However, the synthesized material tested was far from perfect, and the major shortcoming is the reduction of the asphaltene decomposition temperature, which in most cases it occurs at temperatures greater than 300 degrees Celsius. Well, with excellent catalytic properties including oxygen storage capacity, highly active redox property, and a versatile acid-base chemistry, ceria have been proposed to decompose the asphaltene molecules. It was demonstrated that the redox cycle was useful for asphaltene selectivity and conversion over amorphous ceria, and the regenerative capacity of the support allows a continuous asphaltene absorption and decomposition without affecting the performance of the material. Despite the satisfactory results, there are still limitations and challenges to overcome during these processes, since there is not a complete understanding on the oxidative thermocatalytic reaction of the asphaltenes at high pressure conditions. Hence, the shape dependence of ceria-based on catalytic performance for decomposing asphaltenes is the main objective of this work. Further, this research studies exciting topics, including the effect of pressure on non-isothermal and isothermal heating of asphaltenes and the respective kinetic study. Until now, the design of these systems for the application has not been explored. In this research, 3 different nanoparticles with cubic, orthorhombic, and spherical morphologies were successfully synthesized for a simple hydrothermal method. The cubic nanoparticles were synthesized using potassium hydroxide and a cerium nitride hexahydride salt precursor. The orthorhombic nanoparticles were synthesized using the same cell precursor and a polymer PVP in a water ethanol solution. Finally, the spherical nanoparticles were synthesized using the same cell precursor and the polymer in a solution with only water. On the other hand, the effect of the strong metal support interaction was assisted by doping the different ceria nanoparticles with a couple of nickel and palladium in a mass fraction of 1% of each one. Well, as for the characterization of the nanoparticles, the size and morphology was validated through scanning electron microscopy and transmission electron microscopy. The chemical properties were measured by X-ray photoelectron spectroscopy, Raman spectroscopy, and X-ray diffraction. And finally, the surface area was measured by nitrogen absorption-desorption. Well, the nanoparticles absorption capacity for asphaltenes was studied by batch experiments. A stock solution containing 2000 parts per million of asphaltenes was diluted for obtaining solutions with different concentrations between 100 and 2000 parts per million. Nanoparticles were added in a 10:1 ratio of adsorbent mass to solution volume, and the mixtures were stirred at 300 revolutions per minute for 24 hours. The nanoparticles containing asphaltenes were separated by centrifugation, and the supernatant was analyzed in a UV-based spectrophotometer. The amount of the absorbed asphaltenes was determined by this mass balance. Well, finally, high-pressure thermogravimetric analysis were done to evaluate the catalytic capacity of the synthesized nanoparticles. Here were different variables analyzed. The pressure was varied between 0.084 and 6 megapascals. The non-isothermal heating was done at a heating ramp of 10 degrees Celsius per minute from 100 to 800 degrees Celsius, and the isothermal runs were executed at 170, 200, and 230 degrees Celsius. Insights about the kinetic of asphaltene oxidation were realized based on a feeding and order kinetic model. The effective activation energy is obtained from the slope through the plot of natural logarithm against 1 on temperature when 100 of the asphaltene consumption is reached. Well, as for the characterization of the nanoparticles, the morphology and size were validated. The diameter of the spherical nanoparticles was observed as 14 nanometers with a rough surface. The cubic nanoparticles present cubes with a smooth surface and an average size between 14 and 16 nanometers. As for the orthorhombic shapes, are observed with an average size of 20 nanometers, and the structures are highly agglomerated. As for the content of ceria, it increases in the order spherical, orthorhombic, and cubic. Meanwhile, the oxygen content follows the opposite way. As for the high-resolution transmission electron microscopy image, it reveals that the 111 crystal phase dominates the surface of the cubic nanoparticles with an interplanar space of 0.32 nanometers. This is the thermodynamically most stable crystal facet. The orthorhombic are enclosed by the 200 and 220 with an interplanar spacing of 0.27 and 0.19 nanometers respectively. For the X-ray diffraction results, it is observed that with the change in ceria shape, the lattice parameter is slightly affected, being higher for the cubic nanoparticles. Also, the crystallite size through the 111 duration increases in the order spherical, cubic, and orthorhombic ceria nanoparticles. Therefore, crystallinity follows the opposite trend. As for the Raman results, the concentrations of oxygen vacancies were calculated in terms of this ratio and increases in the order spherical, orthorhombic, and cubic. Also, for the doped materials, it was observed that the lattice parameter is reduced regarding the non-doped systems. The reduction of these parameters can be attributed to a portion of nickel and palladium ions may substitute the ceria 4+ in the ceria lattice and alter the unit cell parameter of support since a relatively smaller radio is found for nickel 2+ and palladium 2+ than the ceria 4+. Also, the concentration of oxygen vacancies increase after the doping process due to the increase in the effect size by nickel and palladium ions. From the X-ray for electron spectroscopy results, it is noted that the oxygen ascribed to the surface to lattice oxygen radio increases in the order spherical orthorhombic cubic nanoparticles. Also, the content of the ceria 3+ ions increase in the same line, and the presence of these ions is a consequence of the oxygen vacancies formations, and it promotes the activation and promotion of the oxygen on the bulk and in the surface of the nanoparticles. Interestingly, the amount of the ceria 3+ ions increase with the nickel and palladium functionalization in all samples. The increase in the ceria 3+ proportion ranked as spherical lower than orthorhombic and lower than cubic may infer with the surface modification of oxygen vacancies after the metal loading. The oxygen results corroborate the hypothesis. The content of the lattice oxygen ascribed to the surface was modified after the doping processes. In all samples, the lattice oxygen increases in the same increasing order that the ceria 3+ ions. Well, moving to the nanoparticles asphaltene interactions, it is observed that for a fixed asphaltene concentration, the observed amount increases in different orthorhombic, spherical, cubic, orthorhombic doped, spherical doped, and cubic doped nanoparticles. It has been reported that the systems with palladium and nickel improves the capability and interaction force with the asphaltenes. According to this diagram, the main mechanisms for the asphaltene uptake in the non-doped systems are hydrogen bonding and cation pi interactions. Furthermore, the non-covalent cation pi interaction occurs between the phase of an electron-rich pi system with an adjacent cation like the ceria 3+ ion. Also, the presence of nickel and palladium phases intensify the interaction with the asphaltenes, promoting diverse absorption mechanisms including heteroatom metal interactions and pi-back interactions. Finally, according to the ceria 3 content by XPS results, these parameters follow the trend. The higher the amount of ceria 3 ions, the higher the affinity for asphaltenes due to the reduction of the phalanges absorption potential. And also, the lattice parameter and the oxygen vacancies follows a similar trend between the doped and supports materials. For the oxidation experiments, this figure shows that the asphaltenes without nanoparticles decompose entirely up to 500 degrees Celsius at 0.084 megapascals. When the pressure rises, different changes are evident in the mass change and mass change rate profiles. First, an increase in mass at low temperatures, which is attributed to the oxygen chemisorption in the asphaltene molecular structure, is observed. Then, there is a decline in the sample mass, mainly associated with the desorption and changes in the oxygenated structures formed. Finally, the asphaltenes finish their decomposition at lower temperatures when pressure rises. As for the isothermal analysis, it is observed that with increasing temperature and pressure, the reaction rate is improved for the asphaltene oxidation. However, a conversion of 40% of the sample is obtained in 350 minutes of heating in the best of cases. On the other hand, the catalytic effect of the material is noted in the reduction of the composition temperature of the asphaltenes. The shape of the catalyst appears to have an important contribution to the oxidation of the asphaltenes. Minor but representative changes are observed with the different materials catalyze the reaction. The mass that the asphaltene gains vary as the shape of the catalyst changes, and it is higher for cubic systems, followed by the orthorhombic and the spherical. The Raman, the transmission electron microscopy, and the X-ray for electron spectroscopy analysis demonstrated that the cubic nanocatalysts endowed by the 111 crystal planes present the largest amount of oxygen vacancies, which promote an effective oxygen diffusion from the gas phase or catalyst bulk phase to the surface of the asphaltenes. Therefore, this is the catalyst with more active oxygen for enhance the reactivity of the asphaltenes. Also, the main decomposition temperature peak is observed at low temperatures close to 190 degrees Celsius at 6 megapascals per cubic sample and increases in a lower degree for the orthorhombic and the spherical. As for the catalytic isothermal analysis, it was obtained that the time required to complete the conversion increases in the order spherical, orthorhombic, and cubic. The system that required the longest time was the spherical nanoparticles, which at 0.084 megapascals and 170 degrees Celsius took 150 minutes to convert the 100 of the absorbed sample. On the other hand, the time required to convert the asphaltenes decreases with the presence of nickel and palladium phases. To explain the enhanced activity of the doped materials, two factors are considered. First, the formation and stabilization of high catalytic active sites of nickel and palladium may depend on the ceria facet's crystallographic orientation, which is improved in the cubic nanoparticles due to it is endowed by the 1-1-1 facets. The second aspect could be related to the presence of nickel and palladium lead to factor activation of ceria nanoparticles, which may facilitate the migration of the oxygen vacancies from the bulk to the surface of the ceria nanoparticles. As for the effective activation energy, it is reduced when the nanocatalyst presented a cubic shape, followed by the orthorhombic and the spherical. Besides, the presence of nickel and palladium phases reduce the activation energy values. The results also highlight the obvious effect of the exposed ceria crystal planes, the redox cycle, the content of oxygen vacancies, and the strongest interactions between the nickel and palladium species and the support on the asphaltene oxidation. Well, finally, this work demonstrated that the advantage of structured cubic, orthorhombic, and spherical ceria nanoparticles as new and promising supports with high redox properties for the asphaltene decomposition. Also, it was demonstrated that by exposing more reactive surface, crystalline phases, and ceria 3+ chemical species, it is possible to design improved ceria-based catalysts with enhanced textural and chemical properties. The data also confirms that the presence of nickel and palladium increases the catalytic activity of ceria, reducing the activation energy values in the evaluated scenarios for asphaltene decomposition at different pressures and different temperatures due to the strong metal support interactions. Finally, I would like to acknowledge Professors Camilo Franco, Agustín Cadenas, Francisco Carrasco, and Farid Cortés, as well as the Grupos de Investigación en Fenómenos de Superficie Michael Polanyi and Materiales de Carbono for their valuable recommendations and support. Thank you so much.